Hi, my name is Tom Resh. I'm a specialist in the field of environmental testing, and I've created this video series in order to provide a better understanding of the theory and application behind various types of environmental tests. This current video series is on vibration testing. I hope you find these videos useful, and if you have any questions or comments, feel free to email me at tomvibetest@gmail.com. Thank you.
Today's presentation is on vibration testing, theory, and application. This is part one of a two-part series. Again, my name is Tom Resh. I'm an environmental test specialist, and if you have any questions or comments regarding this presentation, feel free to email me at tomvibetest@gmail.com. Today's topics are: what is vibration testing? What is a vibration test system? Major components of a vibration test system. How does a shaker work? Accelerometer mechanics. Accelerometer selection. Accelerometer mounting. Accelerometer cable handling and usage. Example tools used in vibration testing. Setting up a vibration test system. Mounting fixtures. We will define a servo loop system and do's and don'ts when setting up and performing a vibration test. What is vibration testing? Vibration testing is the input of a vibration excitation into a test specimen by means of a mechanical or electrodynamic shaker. We will go into more detail in this presentation on electrodynamic shakers. Vibration testing is used for many reasons, including to provide an understanding of how a product reacts to vibration input at various frequencies. Now, this is accomplished by performing a sine sweep. When you sweep through a range of frequencies, you will find the resident frequencies of your test specimen, or you will also see how your product reacts at various frequencies. Vibration testing is also used to reduce the cost created by returns due to defective hardware. Some applications of vibration testing are: design verification testing, or DVT, performed on prototype hardware to verify responses calculated in engineering simulations. DVT, or design verification testing, can also be to destruction or to failure testing on your test hardware. You will run the unit at high levels until it breaks in order to see what the limitations are of your test hardware. Qualification testing is performed pre-production to ensure hardware meets customer specifications. Typically, qualification levels are higher than the vibration levels that the unit will actually see in operation or out in the field. This is to ensure that the unit will survive in the customer's specific environment for the operating mode of their system. Production screening testing is also another type of vibration testing. It tests production hardware for workmanship flaws or defects. This is critical in your production process to make sure that your customer is not given a defective piece of hardware. This, of course, will save you money in having to get returns and give the customer replacements, and will also protect your reputation. Production screening is critical for any type of production environment. It will save your company a lot of money in the long run. What is a vibration test system? Well, a crude way of thinking of a vibration test system is the iPod as your vibe controller, a stereo amplifier as your amplifier, and a loudspeaker as your shaker. Now, what the system does not show you is the feedback and control, because iPod cannot collect data and control to the feedback data that it gets. So the two things that are missing from the system would be, you could think of your ear as the sensor as your accelerometer, which will read the or sense the sound generated by your loudspeaker, and then your hand will control the level output from your iPod in order to get it to desired levels. We will go into the servo loop system and more detail about feedback later on in this presentation. Here are some of the major components of a vibration test system. You have a signal conditioner, which conditions the signal inputted from the accelerometer. You have the accelerometer, which is a type of transducer which senses acceleration. You have your vibe controller, which outputs your drive signal to your shaker and also collects feedback data from your accelerometer and adjusts your levels accordingly. You have your amplifier, which amplifies the drive signal and outputs to your shaker. These are the major components of a vibration test system. How does a shaker work? A shaker works on the principle of electromagnetism. It has a field, which has a fixed magnetic field, typically produced by the flow of current through tightly wound wires. So when you power up your amplifier and turn up your gain, you are allowing a flow of current through your field coil, which produces a magnetic field. You then have an armature, which is an electromagnet which has a signal which varies in amplitude and frequency to create the desired vibration spectrum. So when you send a drive signal to your amplifier from your control system, it is being inputted into your armature to produce the desired vibe spectrum for your test. And this all happens due to the fact that force is perpendicular to the flow of current and magnetic field. That is what allows the armature to move up and down. Let's go into more detail about this. And here is Fleming's left-hand rule, which visually represents the force due to the flow of current and the generated magnetic field or magnetic flux. Now, you can see graphically here that force is vertically perpendicular to the current and the magnetic flux. And you can see that the magnetic flux is horizontally perpendicular to the current. So force is vertically perpendicular to the flow of current and the magnetic flux, and current and magnetic flux are horizontally perpendicular to each other. And this is what produces the up and down motion of the armature, this principle. We will now go into detail about the mechanics of accelerometers. Now this is one type of accelerometer. It is called a compression type accelerometer. And how it works is when you apply a vibration in this direction, the mass will compress the sensing crystal, which will cause it to output a charge. There is also another type of accelerometer called a shear type accelerometer, which also has masses and a material which lets off a charge when you apply a shear force to that charge material. Okay, so here we have a high impedance charge type accelerometer. And once again, when you apply a vibration in this direction, the mass compresses the sensing crystal, which causes it to output a charge. Now, a low impedance or voltage type accelerometer works on the same principle. When you apply a vibration in this direction, a vibration force in this direction, the mass compresses the crystal, which causes it to output a charge. Now the difference, a charge type accelerometer will output its charge to a signal conditioner, which converts the signal to a voltage signal, which is then sent to the vibe controller. A voltage type accelerometer has a power supply which powers the ICP, and the ICP is a built-in signal conditioner. So when you create a charge inside of the accelerometer, the charge goes through the ICP circuit, which converts it to a voltage inside of the accelerometer package. So instead of having a big external signal conditioner, you have a small built-in integrated circuit which converts your charge to a voltage, which the vibe controller can then process. And now you can see the axis of sensitivity would of course be this direction, because your materials will generate a charge in this direction. This is the axis of sensitivity for this accelerometer. Typically, it will be the lengthwise of the accelerometer. That will be the axis of sensitivity for your accelerometer, typically. Now we will go over selecting an appropriate accelerometer for your vibe test. We will go over the advantages and disadvantages of charge type and voltage type accelerometers. For temperature testing, when you're doing combined environment testing, it is ideal to use a charge type accelerometer, because when you are running extreme temperature ranges, if you are using a voltage type accelerometer, it will possibly fail due to the fact that it has a built-in electronic circuit, which may not be able to handle the extreme temperature ranges of your tests. So when running a combined environment, which is a thermal chamber with a shaker underneath it, which is called a vibe over temperature test, you will want to use a charge type accelerometer, since it doesn't have built-in electronic circuits that can be damaged or become defective during thermal testing. Another consideration is noise and cable length. Voltage mode type accelerometers are not affected by the triboelectric effect. Charge generation into conduction due to rubbing of insulation materials. That is the triboelectric effect, or length of cable. It is not affected by the length of the cable. However, charge type accelerometers are susceptible to the triboelectric effect, and they all are also affected by the length of cable. So the longer the cable, the more it will affect your signal input back into your signal conditioner. So charge type accelerometers are affected by length and can be affected by the triboelectric effect. So once again, charge generation into conductor due to rubbing of insulation materials. When the insulation materials of your accelerometer cable rub, it can produce a static electricity, which will could potentially input a noise signal into your accelerometer cable. So that is another consideration, and why voltage mode can be more robust. The cables are also more robust. It is a lot easier. It is a much thinner cable that can snap very easily. The conductor can snap more easily in a charge type accelerometer, but a voltage mode usually has a more robust cable and is more ideal for production usage whenever possible. Once again, voltage mode cables are less prone to damage. They're more rugged. Okay, now keep in mind the following. Be sure to select proper sensitivity for accelerometer or setting for charge mode signal conditioner. Depending on what type of tests, what the levels are for your tests, you may need to use a lower or higher sensitivity. For low vibration tests, my rule of thumb is under 5 GRMS. You could use a 100 millivolt per G accelerometer. Anything over 5 G's RMS, I would typically use 10 millivolt per G or less. And as you go higher and higher into, let's say, 50, 60 GRMS, you would want to use 5 millivolt per G. And if it's a response, the levels may be even higher. So you might even want to start going into like the shock range or 1 millivolt per G type accelerometers. Okay. Also, stud mount accelerometers should be used whenever possible, especially for your control accelerometers. Now, there's a lot of places that will use glue, and that's okay, but when you're running higher level tests, you risk the possibility of the accelerometer breaking off So that's not good at all for your control accelerometer if it breaks off during a vibration test, because then your test is just gonna run away, and then the shaker will trip, or the controller will abort the test, hopefully before any damage takes place. Also, you want to take into consideration the size of your accelerometer. You may need a lower profile accelerometer if you have a tight fitting space where you need to mount your accelerometer, whether it's for a response or even for a control. So you need to take into consideration and make sure that you have a variety of different sizes of accelerometers in your test lab for different applications. Also take into consideration ground isolation. You will get ground loops potentially if you are not ground isolated. If you're putting an accelerometer onto a bare metal fixture, you will more than likely get ground loops, which you will see 60 hertz, which typically you will see 60 hertz spikes in your test data. So in order to prevent that, you will want to make sure that your accelerometer is case isolated or ground isolated. Also, you need to take into consideration, will routing of the accelerometer cable require a side or top connector on the accelerometer? So if your setup requires you to, let's say you're putting it inside of the accelerometer inside of a channel, you want to use a top mounted or a top connector accelerometer. Or there might be instances where you're putting the accelerometer underneath something, and in that case you would need to use a side mounted. You would not be able to use a top mounted or top connector accelerometer. Okay, when mounting accelerometers, you will want to use at least one control accelerometer. For smaller systems, one control accelerometer is more than enough for your control. When you need to use multiple controls, it is usually for a very, very large test specimen, or when you are using multiple fixtures and doing a batch test. You would want to have an accelerometer on each fixture if you were doing a batch test with separate fixtures for each of your units. But typically, for most small boxes, you could get away with using one control accelerometer. You will want to mount your accelerometer directly to the surface that inputs vibration into the test hardware. So you will want to have it on your fixture, typically as far to the end of the slip table as possible. You would also want your unit to be as far to the end of the slip table as possible in order to utilize the most energy from the vibration test system. Okay, here you have a shaker body, and this is kind of like an x-ray view of the armature. Here you have the bull nose, which is the adapter interface between the armature and the slip table. Here you have a fixture, and here you have a UUT, which is a unit under test mounted to the fixture. And here you have the accelerometer mounted to your fixture. And that's just showing the motion or the direction of motion for your shaker system. And you can see this is a top mounted accelerometer or top connector accelerometer. The cable goes and connects to the top of the accelerometer, and you can see that it is mounted correctly in the axis of sensitivity. Okay, now we will cover something that's very important in a test lab: accelerometer cable handling and usage. Especially in a production environment, when you are running through a lot of units per day, you will run into the risk of having a lot of damaged accelerometer cables, which could be very costly. Here are a few things to keep in mind when setting up and performing vibration tests. Leave slack in the cabling. You will want to leave a small radius in your cable routing when you mount your cable to your accelerometer. If your radius is too short, you will have the risk of kinking and damaging your accelerometer cable. Here is a kinked accelerometer cable due to the fact that the technician used too short of a radius on their cabling routing. Here you have a cable that was crushed. Don't crush cables. Be aware of where your cable is routed at all times. Don't sit a fixture on top of it. Don't torque down a fixture on top of it especially. But be aware, don't step on your cables either. Be aware of where your cables are at all time. And here again is another kinked cable due to the fact that proper radius was not used when routing the accelerometer cable. Okay, here are two tools that are typically used in vibration testing: the foot-pound torque wrench and the inch-pound torque wrench. Both fixture bolts and stud-mounted accelerometer bolts should be tightened to appropriate torques. Example of torque wrenches can be seen in Figure 1, which I just showed you. The inch-pound torque wrench is also used to typically torque down a lot of different types of units. Typically, the bolts that are used will be 1/4 inch or less, and therefore they will have a inch-pound rating on the bolt. Standard 1032 stud-mounted accelerometers can be torqued to the following specifications. For a 1032 stud torque, it is typically torqued to 18 inch-pounds for a vibration test. And your 3/8/16 black oxide steel shaker bolts should be tightened to the slip plate or shaker head at 25 to 35 foot-pounds. This will vary depending on the opinion of the test lab and what their standard is, but it will typically be in a range of 25 to 35 foot-pounds. Mounting fixture or test specimen. Avoid using clamps whenever possible. You will want to bolt down your unit directly to a fixture whenever you possibly can. Clamps is not the proper way of mounting your unit because it could potentially input small shocks into your unit due to the fact that there will be some decoupling and the unit will rattle around inside of the clamps. So avoid using clamps whenever possible. Bolt fixture test specimen directly to shaker head or slip plate. You do not want to have a stack of interfaces. You will only want to use a fixture mounted onto your shaker head or the armature, mounted onto the armature or onto your slip plate, and then you want to have your test specimen mounted to the fixture. Even more ideal is if you could mount the test specimen directly to the shaker. Whenever that's possible, that will give you the best input energy into your test specimen. The length of the bolt should protrude from the bottom of the fixture no more than twice the diameter of the bolt. So if you take two bolts and you put them next to each other, and you put them next to each other, and you look at the diameter of each stacked on top of each other, the length that should be protruding out of the bottom of your fixture should be no more than the length of those two bolts next to each other. Also, refer to a torque table for the bolt that you are using. Always refer to your company standard for a torque spec, or if they do not have it, look up a torque table online to ensure that you are torquing your bolts to the correct torque specification. Torque bolts evenly, starting with center bolts. You want to work in a star pattern, typically, starting with your center bolts and working your way out. This will ensure that the torque is evenly distributed throughout your entire fixture. Okay, we will now go over setting up vibration test systems. Be sure to follow operating instructions provided by the shaker manufacturer for powering up your vibration test system. Always have your company's procedures and work order instructions on hand prior to performing the vibe test. So you will want to know your company's standards, processes, and the instructions and procedures for that particular unit in your possession prior to even touching the shaker. Be sure to follow the operating instructions provided by the controller manufacturer. Once again, if you do not know how to use a particular vibe controller, be sure to follow the instructions in the manual for that vibe controller, or refer as well to a more senior technician or experienced vibration test engineer if they are available. Be sure to energize your controller before energizing your amplifier. The reason for this is you could possibly send a transient signal through your drive cable into your shaker system when powering up the vibe controller. This could damage your shaker and or your unit. So don't ever power up your amplifier or power up your shaker and then energize your controller. Have your controller energized prior to powering up your amplifier. And it is the reverse process for de-energizing or powering down your amplifier and your controller. You will want to first de-energize your amplifier, and then you will de-energize your vibe controller. And once again, it's the same reason. If you de-energize your controller before you de-energize your amplifier, you risk the potential of sending a transient signal, which could have an infinite amplitude, theoretically, into your shaker, which could damage your shaker and your test specimen. What is a servo loop system? A servo loop system is a feedback system. You have a controller which sends a output drive signal to your shaker. You have a accelerometer which senses the signal that is generated by the vibration test system and outputs a signal which is feedback to the vibration test controller. So when you walk up to a vibe controller, you start a test, it sends out an initial drive signal which causes your shaker to start moving. And once your shaker starts to move, your accelerometer senses the acceleration that's being applied due to the force generated by the magnetic field and the flow of current, and it sends back a signal. The controller then looks at the signal and adjusts appropriately to in order to generate a drive level which will give you the ideal levels for your desired vibration test. So once again, the controller makes appropriate changes to drive signal and outputs new drive levels to the amplifier based on the feedback it gets from the accelerometer. So the accelerometer sends vibration response data or signal to the controller, and the controller looks at the signal data and changes the drive in order to get a desired vibration response from the accelerometer. You will want to keep in mind the lines of resolution. Now, for a vibe test, for a random vibration test, you will not look at every single frequency point on your vibration spectrum. You will only look at certain frequency points or certain lines. And you need to keep in mind the number of lines of resolution that you use, because the more lines of resolution or the more frequency points you look at, the more time is required and the more resources are required by the controller in order to analyze the frequency points and control accordingly. So the more frequency points you have, the better control you have, but also the more slowly responding the controller will be to feedback data that it gets from the accelerometer, which can be dangerous because if you have an issue, you may not see it until it's too late. It may not show you on your graph the issue, for instance, a loose unit or a broken unit or whatever, and you will not be able to see that in your data immediately, and it might be too late for you to stop the test. Here are some do's and don'ts when setting up and performing vibration tests. Do: torque down the accelerometer using calibrated preset torque wrench. Do not over-torque the accel or under-torque with a wrench or non-calibrated torque wrench. If you over-torque the unit or the accelerometer, you could drive the stud up into the accelerometer, destroying the accelerometer, or you could strip out the insert or the threads on the stud. Do route accelerometer cable so that the cable is not crushed. Make sure the radius is tight enough so that whipping does not occur, but also make sure that the radius is large enough so that it does not kink, which could potentially destroy your accelerometer cable. Now, what is meant by whipping is, if you have too much slack on your cable, it could whip and create the triboelectric effect, which is the generation of static electricity or static electric noise into your conductor wire, which will give you a bad signal. Don't route the accelerometer cable in an area that is prone to being crushed by fixtures and other equipment. Be aware of your surroundings and how you route the cable. Don't run it across the floor so someone can step on it, and don't put it in an area where there's a high likelihood of someone placing a heavy object into that location. Do torque down the fixture and the unit using calibrated torque driver or torque wrench. Do not over torque fixture using or under torque using Allen keys, wrenches, or non-calibrated torque wrenches. So for your unit and your fixture, make sure you use calibrated torque wrenches. Don't use ratchets, don't use wrenches, and don't use Allen keys, because you could either over torque or under torque your hardware and your test fixture. Do power up controller and then power up your amplifier. Do not power up your amplifier and then your controller. Once again, like we talked about in the previous slide, you could send a transient signal through your shaker, which could create a potentially infinite amplitude signal, which could damage your shaker and your unit. Do power down your amplifier and then your controller. Do not power down your controller and then your amplifier. Once again, you do not want to create a transient signal which goes into your shaker system. Today we talked about what is vibration testing, what is vibration test system, major components of a vibration test system, how does a shaker work, accelerometer mechanics, accelerometer selection, accelerometer mounting, accelerometer cable handling and usage, setting up a vibration test, mounting fixtures, defining servo loop, and do's and don'ts. Thanks for watching this presentation. Please stay tuned for part 2. Again, my name is Tom Resh. I'm an environmental test specialist, and if you have any questions or comments regarding this presentation, feel free to email me at tomvibetest@gmail.com. Thanks again.